thanks for the invitation. Sorry, I cannot make it. I have some visa emergency. So let's say this. I'm from United States, and I'm gonna basically tell you how to take derivatives of SDEs with some difficult conditions. Okay, so the problem is like this. Consider an SDE. So the SDE will look like this. So this is your drift coefficient. This is your diffusion coefficient. Both depend on a parameter gamma, and B is the Brownian motion, and you run your system for a certain amount of time. This T can go to infinity. And gamma is some parameter controlling the dynamics. So if you for a comparison, you can think of an airplane, and this gamma would control the shape of the airplane. And then you have an observable function, which our system has dimension m, so it's a function from Rm to R, and this is the instantaneous objective function. For example, you can think of this. If you're still using the airplane analogy, you can think of this as the drag or lift of an airplane, and we consider the expectation of or the average of the observable evaluated at a certain time t, big T, and you would certainly imagine that this distribution of your process would depend on the parameter gamma, and hence this averaged observable would also depend smoothly on the parameter gamma. And our goal is to find a formula and then an algorithm for the so-called linear response. The linear response is defined as the partial derivative with respect to a parameter gamma, evaluated at gamma equals to 0. Okay? And I use this delta notation to denote this partial derivative. Mentally, you can also think of this as a small perturbation. Okay, so it's a very simple problem. We want to compute this derivative of some average quantity. And where it is useful? It is useful in several scenarios. The first basic scenario is the optimization where you have the optimization is a conventional sense, where you have a well-defined observable function or loss function or objective function. For example, in fluids, you may ask, if I change the shape of the airfoil by a little bit, then how would my average drag or lift change? So if you have this kind of sensitivity or derivative or gradient information, you can use this to do aerodynamic optimization. And similar problems goes into climate or inverse problems. And those are the straightforward applications of linear responses. There are other less obvious but doable applications, such as backpropagation in machine learning. It doesn't work when the system is unstable or you have gradient explosion, but we can make it work. And there are some even less obvious applications where you don't have a conventional objective or loss function. For example, in generative model, you may consider your optimization goal is described by the Warsaw-Stein distance or by a KL divergence. So that's not conventional observable functions, but still it would benefit if you have a linear response result, right? And I say some guidelines which restrict the scope of our work. First, we assume that all of the first-hand quantities, such as the drift, the diffusion, and the observable functions, they are all smooth enough. Okay. And the second restriction I want to say is that we want to consider the things that can work in high dimension, because typically for a dynamical system, the dimension is proportional to the degrees of freedom in your system. And that is typically a very large number. So whatever we work out, we want it to work in high dimensions. And this is typically require us to do things Monte Carlo-ish. This means that we compute a few sample paths, we do some computations on each of the sample paths, and then we average all of the paths. Okay, so that is something we want to do. And the third restriction is that we want truly linearized solutions, means that we truly take derivative of the SDEs or the distributions of the SDEs. The benefit of doing that is that the cost, we can make a choice. We can choose the cost is either independent of the number of observables or independent of the number of parameters. So think of machine learning as an example. Why it uses backpropagation, which is a truly linearized solution, is because there are too many parameters, and you want an algorithm whose cost is independent of the number of parameters, and that is why you want a truly linearized solution. Okay, and give me a second. Oh, did I stop? Sorry, let me share it. All right, we want truly linearized solution, whereas in contrast, there are other set of solutions which does not really take derivative of the SDEs. These can go by different names, such as non-linearized solutions, curve fitting method, or database method. So these methods, the costs are typically proportional to both the number of the observables and the number of parameters. So if you don't have a lot of observable functions, you don't have a lot of parameters, you can consider using this method. I believe Valerio, the next talk will be, well, I guess the next talk should be on such approach, and we restrict our scope and do not consider those. We want truly linearized. All right. So there are three basic methods, and for computing the linear responses, and the first is what I call the path perturbation method, or it goes by different names such as stochastic gradient method or backpropagation method. So the basic idea is to say that I have this FDE, and then what I do when I change gamma, I fix the Brownian motion, and I fix the initial condition, or I know exactly very well what happens to the initial condition, and then I compute how the path is, how a particular path is changed after you perturb this parameter gamma under fixed Brownian motion and under fixed, or very well, initial conditions. Okay, so for each path, when you change gamma, you have a new path, and then you compare the difference between the location of these two paths, and that information would give you a way to compute or to express the linear response. Okay? And this method is good at when the system is very stable or has contracting directions, and it's good at when you want to perturb your initial conditions. But the problem with this approach is that it does not work when the system is unstable or has expanding directions, because this pathwise perturbation, the difference between these two orbits or these two paths would grow too fast, and you need your computational cost would be too large. Or if you're a pure mathematician, you would say that the convergence is the issue. And this issue is also known in machine learning jargon as the gradient explosion phenomenon. So it's good at stable, but bad at unstable systems. Okay, so that's the first basic solution. And the second basic solution, it also goes by different names. I call it kernel differentiation method, or you can call it more likely ratio, or Campbell-Martin-Desarnod, or Maliavin calculus. So the basic idea, remember in the previous page, what we do is that we fix the Brownian motion and the initial condition. So instead of fixing those, here we're fixing the path. We're fixing the path from initial time to the terminal time, and then we compute how. Then we fix this path, and then we can compute how the probability of obtaining the same path would change when we perturb, when we have a different parameter gamma. Okay, so if you compute the probability change, then you can use for each path, then you can use that information to express the linear response. I'm not going to the detail. This is very vague, big picture idea. Okay, so what this method is good at, it is good at when the dynamics has bad properties. In fact, it does not even care about dynamics properties. The system can be highly non-hyperbolic, if you know what it means, because the derivative, now instead of hitting the dynamics, the derivative would hit the probability kernel, which is refreshed at each time step. Okay, so it does not really even care about your dynamics properties. It can be as bad as you can imagine. But the problem with this approach is that it does not really work well when the perturbation is relatively large to the probability kernel. Okay, and these are the two classical scenarios where this happens. The first is that when the noise is very small, is itself very small, and the second is that when you're perturbing the diffusion of the SDEs, because the perturbation at each time step would be basically as large as the probability kernel within each time step. All right, so that's the second basic approach. And the third basic approach is what I call the divergence method or the transfer operator method, because typically if you take derivative of the measure transfer operator, you will get a divergence. And in picture, it will look like this. Basically, you fix the terminal condition and the Brownian motion, and then you go backwards in time and you ask, okay, if I change gamma, then how likely, then how the probability of obtaining this bundle of paths is changed due to changing gamma under fixed Brownian motion and under fixed, either fixed or you know very well what happens to the terminal condition. So basically, you fix the terminal condition and Brownian motion, and then you change gamma. All right, and this is, you can imagine immediately, this is good at purely unstable systems. Okay, because you're going backwards in time, so now unstable going backwards in time is actually stable. And it is also good at if you're interested in perturbations in your terminal conditions or interested in the scores. Okay, but the problem of this basic strategy is that you can, when the system has contracting directions, you cannot really do things Monte Carlo-ishly. So this method is cursed by dimensionality. Okay, so it is good at unstable systems, but bad at stable systems. All right, so naturally you would imagine that we can consider mixing two of the methods, and indeed that would overcome some major difficulties. Okay, I'm going to give you two examples. The first is what I call the path kernel method. The basic idea is that at each time step, we let most of the perturbation on the dynamics, means on the drift and on the diffusion, we let most of the perturbation on the dynamics propagate as the path perturbation. This would lead to the self-cancellation of the perturbations, which is, the scale of the perturbation would be, proportional to the Brownian increment, and that would be too large compared to the kernel, to the probability kernel. But now I let most of the perturbation propagate and self-cancellation. So this and self-cancellate. So that overcomes the issue of the kernel differentiation. And then, moreover, within each time step, I take out a small portion in the scale of delta t out of the path perturbation and throw it to the probability kernel. Okay, so this is small compared to the kernel, but it is enough to tame the unstable growth of the path perturbation. So this solves the problem of the path perturbation method. Remember, we say that it is not good at unstable system, but now we have a mechanism to temper the unstable. And this is the result. And let me say how to use this result. So basically, you compute this SDE under basic gamma equals to 0. You have several sample paths. And then on each path, because you know the Brownian motion, and then you basically, this becomes an ODE on each sample path. You solve this ODE for your path, for a damped or tempered path perturbation V. And then you on each path, you use this V to compute this expression, and then you average this expression over several paths. Okay, and you in general you require this alpha, which is called the schedule process, to be larger than the largest Lyapunov components. This would temper the unstable growth of the path perturbation. All right, and I show you an example on the 40-dimensional Lorentz 96. And this is just the conventional Lorentz 96, but but here the drift is controlled by one of the parameters. And then I added some diffusion, which is controlled by another parameter. And I have a third parameter which controls the initial condition. So I draw, and this is my average drop. This is my observable function, and I look at its average at a particular time. So so let me explain these plots. So these are the average observable functions with respect to draw at different parameters, 3 different parameters, and these black dots are the average observables at this particular parameter, and these short lines are the drift computed using the path kernel method. You can see if you want to do optimization, then what you really want is that you want this short line to reflect the trend of this curve, right? And now, indeed, we obtain the first result. And in fact, if you're interested in the deterministic system, which has no noise, then you can see that here the red dots are computed on system without noise. And what you can do is that you can add some artificial noise, and then you use the path kernel method to compute the linear response of the modified system. And you see that the linear response on the modified system is still useful if you want to optimize the original deterministic system. Okay, this is a simple example, but no previous method works. The pure path perturbation doesn't work because the system is unstable. Kernel differentiation doesn't work, and also Bismuth over CD doesn't work because we're considering perturbation not only on initial conditions, but also on dynamics, and also the path response method that does not work because we don't have very good hyperparameters. Okay, so this is the first example. The second example is a combination of the divergence method and the kernel differentiation method. This is a very recent result. So basic idea is the same. So at each time step, you let most of the score propagate, and you shift only a small portion to hit the probability kernel to tame the unstable. And this is the formal divergence kernel score formula for the scores of FDEs. And it's the same. So you solve for the way to use it is the same. So you solve for several sample paths. Each sample path you solve with covector, the evolution of this covector according to this ODE, and then you average over this new T over several sample paths whose terminal conditions are at the same location to get the score at this location. Okay, and here you would require alpha to be larger than the largest, essentially largest negatively optimal. Okay, and this is a result for scores, and you see that, and I can tell you it's not too far from linear formula for linear response. Okay, so let me give you some criticism of the previous two combinations I showed you. The way to criticize is to say, okay, for the path kernel method, you see it does not involve the divergence method. So what is not good at is that although it allows unstable directions, but you're actually paying you're still paying some cost for the system being unstable or has too little noise. Whereas this is not a problem at all for the divergence method. For the divergence method, being unstable is good. All right. And for the divergence kernel method, you see that you're paying cost for being stable. So that's its shortcoming. And then I previously had some work for the path divergence method. This is basically studied theoretically by a theoretical dynamicist, and I give you a pointwise defined linear response expression for hyperbolic systems by combining the path method and the divergence. But we didn't go over that today. And you can immediately imagine that eventually we want to involve all of the three basic methods. And this is the program I proposed. So I propose to add noise only to local regions in your phase space. And when you're in these three phase spaces, you switch. So these spaces are these places are the places with poor hyperbolizity. And when you are in this space, in these places, you use the kernel method. And when you're out of these places, you use the fast response method, which is a combination of the path method and the kernel and the divergence. And I would imagine that these would further improve all the previous combinations of two methods. All right. So summary. So this is a kind of high-level talk, and I wish I convinced you three things. The first is that there are three basic approaches for expressing and computing linear responses. So basically, you can say different strategies of fixing certain things when you change your parameter, and then you look at what the leftover thing is changed, and that gives you three basic approaches: the path perturbation method, the kernel differentiation, and the divergence. And they have their own unique strengths and shortcomings. And the second thing I want you to remember is that mixing two of the basic approaches could overcome some major difficulties. Okay. And the third thing I wish you to take away is that, because the dimension is typically very high, if you want a numerical algorithm to work in high dimensions, you better do things Monte Carlo. You compute sample path, you can do things on sample path, and then you average over them. Okay. So, and then I showed you two particular examples of combining two of the basic strategies, which is the path kernel method for the linear response of SDEs, and the second is the divergence kernel method for the scores of SDEs. And because these two results combine two separate methods, so they can overcome the shortcomings of each of the method, and it can solve some problems which previous method couldn't. Okay, and this finishes my. Thanks.